They call it data processing, so let's process some data on today's episode of Hi gang, how the heck are you doing? John Lotshaw, Crackpot Computing here, and welcome to Crackpot Computing's Retrocoding, Adventures in COBOL. In this episode, we're going to be taking a look at how you do math in COBOL, the common business-oriented language. Computers are really good at doing math. After all, they're just glorified calculators. So it stands to reason that COBOL, a language that has business-oriented right there in the name, would have ways of doing math. After all, you can't call it data processing if you don't process data. COBOL has two ways of doing math. One is English-like and uses a more verbose syntax to describe what you're going to do step by step. The other is algebraic, which is more like what you would find in other computer languages like C or JavaScript. The first method uses English-like statements like add, subtract, and multiply. Look at this example. Add 1 to counter. This will increase the value in counter by 1. If counter is 0, then counter will then be equal to 1. Next time it's executed, counter will be equal to 2, and so on. Now, look at this. Multiply subtotal by sales tax rate, giving sales tax amount. This code will take a value, subtotal, multiply it by sales tax rate, and store the result in sales tax amount. For example, if subtotal is $100 and sales tax rate is 7.5% or 0.075, then 7.5 or 100 times 0.075 will be stored in sales tax amount. That value can be used in other calculations, for example, being added to the subtotal to get a final total for an invoice. The second way of doing math allows you to write out a complex equation using notations like you'd find in other languages like BASIC, Pascal, C, or JavaScript. Let's use our sales tax example, this time using the compute verb. Compute total equals subtotal plus subtotal times sales tax rate. Using the verbose method, we'd get an interim value, sales tax amount, which would then be used in another calculation to compute a total amount. And you may still want to do this, like say you're printing out an invoice and you want to show how much tax, not just the tax rate, but the amount paid is. But here, we can do that whole calculation in one fell swoop. If our subtotal is $100 and the sales tax rate is 7.5%, the sales tax amount is calculated first because it's inside the parentheses, then added back to the subtotal to give the final total amount. It's much more straightforward and doesn't have the multiple steps that can get confused and mixed up, as we're about to find out. Let's create a program that will calculate all kinds of values related to a circle. It'll ask for a radius, and from that, it'll use COBOL's math functions to derive all the other values having to do with circles and spheres. Okay, we're here in Visual Studio, and we're in our COBOL directory. Let's start by creating a new blank file, and we'll call it circles.cob. And let's start by putting in our usual COBOL stuff. So we'll start with identification division. call this circles. And let's set up our data division working storage section. And we'll come back and we'll fill this in just a moment. Next we have our procedure division, and then we'll just put a stop run in here, but we'll fill this out momentarily. All right. First thing we want to do is set up our working storage. Now we're going to use what's called a 77 level variable. Previously we used an 01 level, but we could have been using an the 77, because the 77 level is basically just intended as scratch working space. You can't have levels underneath it. You can't divide it up into sub variables like a record. So it's really intended for this purpose, for what we're going to be using it for, which is working scratch, memory only computations and variable and data storage. Back in the day, there was a real reason to do this, because there was a difference between the working storage and 77 level and the 01 level down at the way that it was implemented at the processor level, but nowadays not so much. But we're going to use them anyway. So the first thing we're going to do is we're going to set up the variable that we're going to put our radius in. So we'll do 77 radius, and we'll come out here and we'll define this as pick 10.910. And what this is going to be set aside a 9-digit number, actually a 20-digit number, with 9 of the digits for the integer portion, I believe that's the mantissa, and then the 10 digits for the fractional part of the number, because we are going to be working with fractions here. And here's one of the most famous ones in the world, and pi. Now we're going to set this up as a constant. Now you don't really have constants in COBOL, but you can kind of fake them by assigning a value at this time in the working storage section, and that's what we're going to do. So we're going to set this up as with 1 digit to the left of the decimal, which is going to be the 3, and then 9, and then 10 digits. There we go, 10 digits for the fractional part, and then we'll use this clause value and assign it the famous 3.14159265535. Now we could go and change this in the program, but we're not going to. We're just going to kind of leave that alone because, well, pi is a universal constant. Now let's set up some variables to work with the, since we're going to be working with areas and volumes, we need to, it'll be nice to have places where we can put the calculations based on the radius squared and the radius cubed, because we're going to be using those over and over again. So let's go ahead and set those up. And in fact, let's, we can copy this because we're going to use this a lot. And let's do our cubed. Now we're just setting up the results for all of our different results. So, like for example, we'll have circle diameter, and the area. And these are all just standard picture clauses. And we'll do one for the sphere area, the area of the surface of the sphere. And we'll do one for the volume of the sphere. And since we're going to have, in one of the calculations, we're going to have to do 4 thirds. Let's just go ahead and define that as one of our pseudo variables like we did with pi. And again, we'll just go ahead and assign it the value of 1.3. Make sure we got, let's see, 3, 4, 5, 6, 7, 8, 9, 10. Okay, that takes care of all of our variables. Now, let's go and start coding. So the first thing we're going to do is we're just going to put a little introduction here. So display. And here is the prompt. And as we did last time, we'll do this with no advancing so that it doesn't put a carriage return at the end of that sentence. And we'll immediately accept the radius. Now let's display. Now let's start calculating and displaying the various calculations for these parameters for the circle based on that radius. So the first thing we're going to do is we're just going to display the radius as it was put in there. So let's display put a bunch of spaces out here so that we have enough room for so that everything lines up nice and neat. And we'll put radius here. Okay, the first thing we're going to do is we'll calculate the diameter of the circle. And the diameter is just the radius times 2. So what we're going to do is we'll use the multiply giving statement. So it looks like this: multiply radius by 2, giving circle diameter. What it'll do is it will take the value in radius, whatever we entered in up here, multiply it by 2, and then we'll store that in the circle diameter variable. Now let's display it. Got to spell diameter right. Actually, I don't, because this is the display, but helps to be neat. So now we'll do circle diameter. Here it does matter how I spell it. All right. So the next thing we want to do is calculate the area of the circle, and that is given to us by the formula pi r squared. So the first thing we're going to need is r squared, and that's simply r times r. So let's do, again, another giving, multiply by giving, by doing multiply radius by radius, giving r squared. Now there's a value in r squared, and we can use it in another calculation, which will be the actual area calculation. And that will look like multiply pi by r squared, giving circle area. And let's display it. So that is the famous pi r squared for this area of the circle. And this is in square units. Now, I forgot to put one in here, so let's go back and put it in, and that is to do the circumference of the circle. And that is 2 pi r. Well, 2 times pi times r is the calculation. 2 times r is the diameter, so we already have that number in here. So all we need to do is multiply the diameter by pi. Multiply circle diameter. This is the same type of statement that we've used before all through this, which is going to be the multiply by giving. So multiply circle diameter by pi, giving circle circumference. And I'm going to let Visual Studio spell it for me. Now, circle circumference in units. Circle, there it is right there. Okay. So now we've got all of the two-dimensional calculations. Let's do the three-dimensional, which is a sphere based on the same radius. So we're just going to put a blank space in here to separate them. Now let's get the area of the surface of the sphere. The formula for calculating the surface area of a sphere is 4 pi r squared. So we need to do this in 2 steps here, and we will do that by, first, let's multiply pi by 4, and we'll use the multiply by giving to do this. So multiply by pi by 4, giving sphere area. Now we have a value, sphere area, which is going to be equal to pi times 4. Now we're going to use a slightly different version of the multiply statement. What we're going to do is, will look like this: multiply sphere area by r squared. What will happen is that the value that we get out of this calculation, and it's multiply, not multiply, multiply by the value that we get out of this calculation here will then be multiplied by r squared, which we had calculated up here, and then put right back into sphere area, overriding the old value. So this is the same thing essentially as saying this. But the proper way to do it is just to do this. So now we have the so let's write down our header here and display that. Now we want to calculate the volume of the sphere. The formula for the volume of a sphere is 4/3 times pi times the radius cubed. So, first thing we need to do is get r cubed, and that's r squared times radius. So let's do that first. And we'll put it in r cubed. Next, I'm going to multiply pi times r cubed, and that will give us the first part of the sphere volume. So let's multiply pi by r cubed, giving sphere volume. Now we're going to do the same trick that we did just a moment ago with the sphere area. We're going to take sphere volume and just multiply it by the 4/3 constant that we'd set up earlier, and then put that right back into sphere volume. And now let's display it. This is in cubic units. And that should be everything we need. So let's save this. And let's see what happens. And I've got some errors here. Lots of errors. What have I done wrong? Okay, well, I have no idea what happened there. Probably, if you see what I did wrong, please put it in the comments. But the 77 variables are working now. Now, I did have the period in here, which I don't know why I did that, but I did. Anyway, it should be a V. The 77 level variables are working, and there is one typo in here. This is right here on line 35. I forgot to put multiplied by 4. So it was just multiplied by whatever. So it was hitting given, and it didn't know what to do with it, so it threw the syntax error. So this should compile. And it does. Okay. Let's take a look at our program. Let's see what we've got written here. So now we'll run circles. So what is the radius of your circle? Well, let's just say 1. That'll be easy to check. And there we go. Radius of the circle in units is 1. The diameter is 2 times the radius, which is 2. The circumference is 2 pi r, so that's 3.14159263535 times the diameter, which is 2. So that's tau, for those of you keeping score at home. And then the circle area is pi r squared. R squared is 1, because 1 squared is 1, so it's pi. Then our surface area, and those numbers look good. I don't know, can't do the math right off the top of my head, but those look right. Now, as you can see, it doesn't look very good because there's a lot of leading zeros in there. So we can suppress those by using a new thing in the picture clause. And let me show you what we're going to do. So to do this, we're going to go back up here to the picture clause, and we're going to create a numeric edited value. This is basically going to take a number, turn it into a string of characters, and then format it however we tell it to do that. So let's do that really quick, but let's just create a new variable, another new 77, and we'll call it display value. And we want it to be pick. Now here's the tricky part. It's going to be Z, which means suppress leading zeros, 9 characters, and then a 9. We've got a 10-digit character field in there. We always want to show, even if it's a 0, we want to put that first character just to the left of the decimal point. But all the other zeros, we want to suppress them. And then we'll do 9, 10 characters for the fractional part. Now, what we have to do is, since we can't turn all of these into into a suppressed 0, because we have to use them in a calculation. So what we're going to have to do is temporarily move our results into this display value, and that's what we will display. And to do that, we'll use the move statement. So we'll just move, in this case, radius, since we're going to be displaying the radius, move radius into this display value. And then we, instead of displaying the radius directly, we'll display value. Now let me show you what it's going to do. You see how we've got all of these zeros in here. If this works, then it'll display the exact same number, but all of those leading zeros will be turned into spaces. So let's run the compiler. Oh, and it's not move into, it's move to. So let's try that again. That worked. Now let's see what our results are. And let's do again 1. And ooh, it did not put, oh, and I think I know what the problem is. It did not put our decimal point in there, but I think here it needs to be the period. It won't, because this is not an actual number, which is what the V is used for as the decimal point for. This is a string. So let's try that again. And let's compile it and run it.
Yay!
There, that worked this time. That is correct. That is exactly what it should look like. So now we can go through and add this move statement before each one of these displays, after each calculation, and change it to display, use the display value as the temporary value to display. Now that we've got all of those modifications made, let's go and recompile it and run it. And this time it should display with blanks instead of all of those zeros.
Hooray!
There we go. That looks a lot better. Now, since we got 10 digits in here, we can put some pretty big numbers in here. Let's run it again, and let's say our radius is going to be 5,000 units. As you can see, we can handle some big numbers. But we still have a slight problem here because that is not right. So let's see what's going on there. All right, so after going down a rabbit hole, I discovered, yeah, this was right after all, because The problem wasn't my code, it was the numbers I was putting in. Well, not so much the numbers I was putting in, it was just giving me something misleading. Here's what was going on. I was using as a test of a big number, 5,000. And the sphere surface area that it was giving me was this kind of ridiculous number, which was pi times 10 to the 8th. Well, here's the thing. If you put in 5,000 for the size of a sphere, you get pi times 10 to the 8th. Yeah, because 5,000 squared is 10 to the 8th times pi. Okay, it just looked wrong, but it wasn't. It was right. It was working. So that's one of the fun parts about programming. All right, so we've got the leading zeros suppressed. We need to do something about how verbosity of this, and this was kind of what was leading me down the rabbit holes earlier. So let's use the compute statements to simplify and rework all of this math. And we really don't need to do it up here in the circle. Let's just do it here in the sphere. And let's replace these two, which again were driving me buggy, with the equivalent compute statement. So what I'm going to do is I'm going to comment these out, and this is how you create a comment in freeform COBOL. And let's replace that with compute sphere area equals 4 times pi times r squared, since we already had that up here. And then let's replace, now we're going to keep this r squared to r cubed, but let's replace this statement and this statement with the equivalent compute statement. So let's comment these out. And let's replace it with compute sphere volume equals 4 times 3. And I could put the constant that we've already defined, but I'm just going to go ahead and do it right here. Times pi times r cubed. So we've condensed two statements into one. The result should be exactly the same. We'll put 5,000 in here, and the numbers are not the same because I've done something wrong here. What did I do wrong? Okay, again, we went down another rabbit hole because of precision. There were only, the problem is that by putting in 5,000, overflowed the 10 digits that we had, because 5,000 squared is an 11-digit number. So, by going back and making sure we just don't put in a number that big, this actually works properly. So let's go ahead and compile it again. You can see we didn't have any errors. And let's put in 500 500, not 5,000, 500 for the radius of our circle. And as you can see, our sphere volume is correct. But we're really pushing the limits, starting to push the limits of our precision, so we've only got 10 digits here. The solution would be to go and put more digits in here. But I'll leave that as an exercise to you. So we have a nice little program that will accept a radius and then calculate all the different parameters of circles and spheres based on that radius. That compute statement sure made things a lot easier, even with the simple equation that we were doing here. I mean, we were just doing basic arithmetic, but COBOL has functions to do much more complex math, like trigonometric functions and financial calculations. We'll be doing more complex math in the future, but I just want to give you a quick overview and idea of how math works in COBOL. I hope you've enjoyed this episode. I've had a blast putting it together for you. Please make sure that you click subscribe and hit the bell to get notified when new episodes of Adventures in COBOL get posted. And also, don't forget to like the video. YouTube likes it, and we like it when you like it. That's a lot of likes. Anyway, please tell your friends and other people that you have contact with on the internet. Social media is great, but the original social media was word of mouth. And I would really appreciate it if you would help spread the word about Adventures in COBOL. Until next time, this is John Latshaw for Crackpot Computing saying, happy coding.